So today is going to be our last day of L'Hopital's rule. Okay, so it's day 3. And now we're going to start looking at, okay, so what do you do? How do you figure out when it's 1 to the infinity? Because it's not necessarily 1, and 0 to the 0, and infinity to the 0. So these infinities can be either negative infinity or positive infinity. So 1 to the negative infinity or even negative infinity to the 0. Okay, so one thing we got to realize is that we have always said anything to the 0 power is 1, right? Well, no, 0 to the 0 power isn't necessarily 1. And also infinity, some type of infinity raised to the 0 power is not 1. Okay. And 1 to the mean. Now this one is the one that blows me away the most. Okay. And we're gonna see in just a minute that how it's not true. Okay. But 1 to the infinity, you would think 1 multiplied with itself an infinite number of times would still be 1, but it's not. Okay. And it has to do with the exponents and all that. Okay. So let me show you what we need to do. Okay. So whenever they take on this form of 1 to the infinity or 0 to the 0 or infinity to the 0, what we're going to need to do is this is causing a problem. So what we're going to do is we're going to get the exponent out of there. And the idea behind that is to take the natural log. Okay. Because if we take the natural log, then anything that's a power can come down and we can multiply by that power. Okay. So it's a logarithm property, basically, we're looking to use for this. Okay. So what we're going to do is we're going to take the function that we're trying to find the limit of, and we're going to take the natural log and we're going to look at that limit. Okay. And so, and then we're going to switch it back out. Okay. So like, let's say we have a function like this. Okay. We can rewrite this as e to the ln of the function because these are going to undo each other. And this is the idea behind it. These are going to undo each other. So this is still the same limit. Okay. And then if we take the limit of e to a power, then that's just e to the limit of that power. Okay. Which is this. And this is what we're going to find. Okay. And so we need to find this limit, the limit of the natural log of our function, because we're going to be able to replace it and get our answer. Okay. So let me go through this with you because I know, like, what did you just say? All right. Okay. So if we look at this, okay, if we try to do direct substitution, this is going to be 1, and this is 1 over 0. Okay. And so what this is going to give us, if we try to do this, is it gives us 1 to the infinity. Okay. And so we have to determine what that is. Okay. So whenever we get one of these, we're going to let f of x be this function we're trying to find the limit of. Okay. So we're going to let f of x, I should write we're going to let f of x equal x to the 1 over x minus 1 power. And then what we're going to do is we're going to take the natural log of both sides. So that stays equals, right? All right. And what that's going to allow us to do is bring this power down in front because that's a logarithm property. So now we have ln of f of x is equal to 1 over x minus 1 times ln of x. Okay. Or ln of x over x minus 1. Okay. All right. So now what we need to do is we need to find the same limit as x approaches 1 of this function. Okay. So we're going to find the limit as x approaches 1 of ln of f of x. And so that's the same as the limit as x approaches 1 of natural log of x over x minus 1. And now we try, okay, so now we're working on this. We can forget this for a minute. Okay, let's work on this. If we try to plug 1 in here, the natural log of 1 is 0, and this would be 0, right? So if we try to do direct substitution with this limit, we're going to get 0 on top and 0 on the bottom. That means that we need to write the limit as x approaches 1 of ln of x is equal to 0, and the limit as x approaches 1 of x minus 1 is also going to be 0. So we have 0 over 0. And so we can use, this is where we use L'Hopital's rule. Okay. All right. So the derivative natural log of x is 1 over x. So this becomes the limit as x approaches 1 of 1 over x over, and the derivative of x minus 1 would just be 1. So this would be the limit as x approaches 1 of 1 over x. And so that just becomes equal to 1. All right, because we can do a direct substitution, and 1 divided by 1 is 1. Okay, so now how do you use this, right? Because we know, I should write, actually probably should write the 1 right here. So what we know now is we don't have this limit yet, but what we do have is the limit as x approaches 1 of ln of this function. Okay, and we know that that comes out to be 1. So here we go. Let me show you how we're gonna do this. Okay, so we're gonna start with this, okay, which is the limit as x approaches 1 of x raised to the 1 over x minus 1 power. Okay, now that was f of x, right? So, right, because we can replace this with f of x. So this means the limit as x approaches 1 of f of x, those have to be the same because f of x is this function right here by up here. Okay, now what I'm going to do is take the natural log of it and exponentiate it because they undo each other. So this can be rewritten as the limit as x approaches 1 of e to the ln of f of x, because e to the ln will cancel out, and this is the same as f of x. So this is the same as this, and this is the same as this. Therefore, this and this are the same. Okay. Now, this is the limit of a composition, so we can take e raised to this power, right? And we're going to take the limit of this. So this one becomes e to the limit as x approaches 1 of ln of f of x. And from what we just figured out up here, that turns out to be 1. So this is actually equal to e to the first power, or this is equal to e, the number e. So 1 to the infinity, I mean, you would think 1, like I was saying earlier, 1 to the infinity, like 1 multiplied infinitely many times together should equal 1, right? Nope. In this case, it's equal to e. All right. All right. And all of this is true. Okay. All of this works. All right. So it's not like hocus pocus. All right. It may seem like it, but it's not. It's all based on if this is true, then this must be true. And if this is true, then this must be true. Right. Okay. So it's based on logarithm properties, it's based on limits, and it's based on L'Hopital's rule. Okay. But the key here is we got to find this, the limit as x approaches 1 of the ln of the function that we're trying to find the limit of, right? We're always going to call this one the function. Okay. And then to get it, right, we switch the actual function to f of x, and then we're going to e raised to the ln because those are going to undo each other. And then we take the limit of this. I mean, if you skip this step, that would be okay. All right. All right. I'm going to do the next one. This one was fairly straightforward, fairly easy. I mean, a lot of things to think about. All right. But not much, not very hard to work it out. Okay. So the next one's a little bit harder. And then I have 3 examples today. Excuse me. I'm sorry. I couldn't pause my recording for my sneeze. Sorry. Okay. So example 2 is going to be a little bit harder. And then example 3 is goes back to being a little bit easier. Okay. All right. So for this problem, we're going to try and find the limit as x approaches 0 from the right of sine of x raised to the x. So if we try to do direct substitution, this would be sine of 0, which is 0, raised to the 0 power. So what this is giving us is 0 to the 0 power, right? And so that's one of the ones where, okay, we can't determine it, right? It's undetermined what this actual value is. It's not necessarily always going to be 0, like 5 to the, or 1 rather, sorry, 1. So like 5 to the 0 is 1, 6 to the 0 is 1. 0 to the 0 is sometimes 1 and sometimes it's not, okay? So what we're going to do is we need to, the problem is this exponent right here, right? This x right here. So we need to get it down. And the way to handle that is to take the natural log, all right? So we're going to let f of x equal sine of x raised to the x. And then we're going to take the natural log of both sides. which will give us the natural log of sine x raised to the x. And using logarithm properties, I can rewrite this as x times natural log of sine x. So ln of f of x is equal to x times ln of sine of x. And now we change it into a product. Okay. So now we want to find this limit. All right. So then we can do the substitutions that we talked about earlier. Okay. So let's find the limit as x approaches 0 from the right of ln of f of x, because we're going to be able to use this in our problem. Okay, so this becomes the limit as x approaches 0 from the right of x ln of sine x. So x times ln of sine of x. All right, so as x approaches 0, this is getting closer and closer to 0. So what we have is, from this, we have 0 times, and as x approaches 0, okay, sine of x gets closer to 0. Okay, so this is getting closer and closer to 0. That means ln of, this is getting closer and closer to 0. How sine of x is getting closer and closer to 0? It's coming from the positive side, all right? So that means the natural log, what we're putting in the natural log, is getting closer and closer to 0, but it's positive. And from the graph of ln of x, we know that that is equal to negative infinity. Okay, so we have the situation where we have a product, right? But we need a quotient to use L'Hopital's rule. So the way we're going to fix this is we're going to multiply. We're going to get rid of this. We're going to multiply by 1 over x over 1 over x. So this limit becomes the limit as x approaches 0 from the right of x times ln of sine of x times, and it would be 1 over x over 1 over x. And so when I multiply this times 1 over x, I just get ln of sine x and over this, okay? So this is equal to the limit as x approaches 0 from the right of ln of sine of x over 1 over x. Okay, so here what happens is, if we try to put 0 in here, okay, we get sine of 0, and it's not what it actually equals at 0, which is going to be 0, but what's it getting closer and closer? How is it getting closer and closer to 0? It's getting closer and closer from the positive, right? Same reason for this one, why this one was, or this one right here, why it was negative infinity. This is going to be negative infinity again, okay? So we have the limit as x approaches 0 from the right of ln of sine x is equal to negative infinity. Now, when this x is getting closer to 0 from positive values, right? Because they're all going to be positive. This is going to get really, really small, but it's going to be positive. And so when we take 1 divided by that really small positive number, that's going to be really, really big overall. So this is the limit as x approaches 0 from the right of 1 over x, and that's actually positive infinity. So because we have some type of infinity over some type of infinity, that means we can apply L'Hopital's rule finally, okay? Now, to use L'Hopital's rule, I'm going to rewrite this. This would be easier if we think of this as being x to the negative 1. All right, so taking the derivative of this, all right, the limit as x approaches 0 from the right of, and the derivative of this would be 1 over whatever you're taking the log of, so that'd be 1 over sine x times, and then cosine x over, okay, and this would be negative 1 times x to the negative 2 power. Okay, so really this is, I'm going to come off to the side here, this is the limit as x approaches 0 from the right of cosine of x over sine of x, big fraction bar, over, and this would be negative 1 over x squared. Okay, and what I'm going to do next is I'm going to do a little bit of algebra. I'm going to get rid of this complex fraction. So I'm going to multiply top and bottom by x squared and also sine x. So I'm going to multiply by x squared sine x. Let me say one thing really quick. Let me write this. You may be thinking, oh, let's switch that to cotangent x. And you could. You could, all right? And you're going to see on some of the problems I did, what's going to happen is if you switch this to cotangent x, it's going to take us longer to get to the answer, okay? So how do you, it's just experience of working these out when you start to realize, okay, switching it to cotangent x would actually make it harder, okay? So what's this is, here's why. We want to keep it cosine x and sine x because we can do direct substitution, all right? And we can get some values out of this, all right? So right here, we're going to wind up with x squared cosine x. So this becomes the limit as x approaches 0 from the right of x squared cosine x over, and then this would be just negative sine of x. Okay, so when we go to do the direct substitution, well, sine of 0 is just 0, and 0 squared is 0. So we're going to wind up with 0 over 0, right? Okay, so this is a case where we're going to have to apply L'Hopital's rule again. All right, so this becomes the limit as x approaches 0 from the right of x squared cosine of x, and that's equal to 0 because we have a 0 right here. And we also have the limit as x approaches 0 from the right of negative sine of x, which sine of 0 is 0, so this is also going to be 0. So we have 0 over 0, L'Hopital's. Now, what we're going to have to do here is we're going to have to apply the product rule, okay? And then derivative of this, right? Because the L'Hopital's rule just says take the derivative of the top and take the derivative of the bottom and plug your 0 in, all right? So this is equal to the limit as x approaches 0 from the right of the derivative of this would be 2x, the derivative first, times the second function, which would be cosine of x, and then plus x squared times the derivative of cosine x, which is negative sine x, all over negative, and then the derivative of sine x is cosine x. Okay, so then this is, let me slide it up a little bit. This is equivalent to the limit as x approaches 0 from the right of 2x cosine of x minus, right, because when you multiply those, you get minus x squared sine of x. Okay, guys, I wish I hadn't put parentheses around there, but I did, all right? Okay, over negative cosine x. Okay, so we're going to try to plug in 0 in here. So this would be equal to 2 times 0 times cosine of 0 minus 0 squared sine of 0 all over negative cosine of 0. Well, because cosine of 0 is 1, this is going to be 0. So this is equal to 0 minus, and this is going to be 0. And cosine of 0 is 1, okay, but we're taking the negative of it, so it'll be negative 1. So we have 0 over negative 1, which is simply 0. Okay, so what is that telling me? Okay, that's telling me that the limit as x approaches 0 of ln of f of x is 0. Okay, so I'm going to write that. So the limit as x approaches 0 from the right of ln of f of x. That was a long time to get there, right? It took a while. And that's equal to 0. So now we know that's equal to 0. So now what were we trying to find? We were trying to find the limit as x approaches 0 from the right of sine of x raised to the x. Okay, and that was the same as writing the limit as x approaches 0 from the right of f of x, because we called f of x this function. And then what we're going to do is we're going to say, all right, so that's the same as the limit as x approaches 0 from the right of e to the ln of this. Because once again, e to the ln are going to undo each other. That's going to allow you to take the limit of just this. So this becomes e to the limit as x approaches 0 from the right of ln of f of x. All right. And then what we just realized is we just figured this one out, right? And that was the whole idea, is we found this limit and we know that that is 0. So now this whole thing can be replaced with 0. So this is e to the 0, and e to the 0 is 1. So the limit as x approaches 0 to the right of sine of x raised to the x turns out to be a value of 1. All right. So this would be the hardest, one of the harder problems to do. Okay. It just takes a while to do. All right. All right. So I promise this one's going to be easier. Okay. It's not going to take quite as long to find the limit as of ln of f of x. Okay. So what makes this a little bit easier is because this exponent is 1 over x. So when we bring the power down, it automatically goes to becoming a quotient. That's why. Okay. So if we're trying to do infinity, right? So this is going to be infinity raised to the 1 over infinity, right? So we're talking about a big number. So a big number raised to 1 over a big number. 1 over a big number, that's going to be, that right here is going to be close to being 0. Okay. So what we have this time is we have infinity raised to the 0 power. Okay. And so I wanted to go over like one of each of these to show you how you go about doing it, right? But they're all really, you go about doing it the same way, okay? All right, so what we're gonna do is we're gonna let f of x be this function that we're trying to find the limit of. So let f of x equal, because that's gonna allow me to replace that with f of x and then e to the ln, right, of that. So this is f of x is equal to x to the x raised to the 1 over x power. If I take ln of f of x, that'd be ln of x raised to the 1 over x power. This can come down. So ln of f of x is equal to 1 over x times ln of x. And that means ln of f of x is equal to ln of x over x. So coming back over here, or see how it automatically becomes a quotient instead of like a product. That's what was hard about the last one, is this became a product, right? And then you had to make that product become a quotient, okay? So right here, we want to find the limit as x approaches infinity of ln of f of x. And then we're going to use this limit to figure out this one, okay? So this is the limit as x approaches infinity of ln of x over x. Okay, so what happens when x approaches infinity? Well, the graph of ln of x, as x gets bigger and bigger, the graph keeps growing, right? Up, 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 right? So this is going to be infinity, and this one's also going to be infinity. So what we have is infinity over infinity. So we got to write the limit statement. So the limit as x approaches infinity of ln of x is equal to infinity, and the limit as x approaches infinity of x is also equal to infinity. And because we wrote this, now we can apply L'Hopital's rule, okay? So the derivative of ln of x is 1 over x, and the derivative of x is just 1. So this becomes the limit as x approaches infinity of 1 over x. So x is getting really, 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 really big, right? So this is big but positive, right? So this is going to get closer and closer to 0. So this is equal to 0. All right, so now we know what this limit is. Okay, so we can say, all right, the limit as x approaches infinity of x raised to the 1 over x power is equivalent to the limit as x approaches infinity of f of x, which means that can be rewritten as the limit as x approaches infinity of e raised to the ln of f of x, because they're going to do each other. And then because it's e to this power, here's where the function part is. So I'm just going to take the limit of this. So this is equal to e raised to the limit as x approaches infinity of ln of f of x. And what did we just figure out? We just figured out that this limit came out to be 0. So this is equal to e to the 0. And e to the 0 power is 1. Okay, so the value of this is 1. All right, kind of crazy, huh? All right. All right, guys, I hope that went kind of fast for you. It just takes a little bit of time, okay? All right, we'll meet back.